Sugar occupies a paradoxical place in the story of the human brain, a substance both essential and potentially destructive. On one hand, glucose is the brain's primary energy source, especially during early development. In infancy and childhood, the growing brain consumes a disproportionate share of the body's glucose supply to support rapid synaptogenesis, myelination, and neurogenesis. Without adequate glucose availability, key processes such as memory consolidation, emotional regulation, and executive function may be impaired. In this context, sugar, particularly in the form of blood glucose derived from complex carbohydrates, is not merely a dietary component, but a neurodevelopmental necessity. However, the very system that relies so heavily on glucose during early life can later be undermined by its chronic overabundance. Emerging research paints a troubling picture of what happens when glucose metabolism is persistently dysregulated. In older adults, excess circulating glucose, often the result of diets high in refined sugars and ultra-processed carbohydrates, has been associated with increased risk of cognitive decline, dementia, and Alzheimer's disease. The mechanisms are increasingly well understood. Chronic hyperglycemia can impair insulin signaling in the brain, contribute to neuroinflammation, and promote the misfolding and aggregation of key proteins implicated in neurodegeneration, such as beta-amyloid and tau. This duality, the early dependence versus long-term vulnerability, deserves deeper biochemical scrutiny. During early development, the brain's glucose demand is tightly regulated, and its uptake is mediated by specific glucose transporters like GLUT1 and GLUT3. These transporters ensure a steady, responsive supply that meets the rapid energy demands of growing neurons. But in adulthood, especially under conditions of insulin resistance, these same transporters can become dysregulated. As insulin signaling in the brain weakens, neurons may become less efficient at metabolizing glucose, leading to energy deficits even in the presence of plenty. In response, cells may experience oxidative stress, impaired mitochondrial function, and a breakdown in the brain's glymphatic waste clearance system, key events in the cascade toward neurodegenerative disease. Compounding the problem is the role of advanced glycation end products, AGEs, which form when proteins or lipids become glycated through prolonged exposure to high glucose levels. AGEs have been shown to cross-link with tau and beta-amyloid proteins, making them more prone to aggregation and resistant to normal cellular clearance. This suggests that chronically elevated sugar intake doesn't just supply excessive energy, but may directly contribute to the toxic burden inside the aging brain. These effects are not merely theoretical. Brain imaging studies have linked high-sugar diets with reduced hippocampal volume and impaired functional connectivity, both early warning signs of Alzheimer's disease. But while the long-term risks of sugar excess are significant, it is important not to overlook its critical developmental role. Infants fed glucose-enriched formulas show improved growth metrics and enhanced early learning capabilities. Glucose is required for neurotransmitter synthesis, particularly acetylcholine and glutamate, which are central to learning and memory. Moreover, acute glucose administration in both children and adults has been shown to enhance short-term memory and cognitive performance under certain conditions, such as sleep deprivation or high cognitive demand. This reinforces the notion that glucose, like oxygen, is a powerful but potentially volatile biological fuel, essential when used wisely, harmful when chronically mismanaged. A cautionary takeaway emerges. Not all sugars are equal, and not all brain periods are equally vulnerable. While complex carbohydrates and natural sugars in whole fruits, vegetables, and grains release glucose steadily and support long-term neurological health, frequent consumption of added sugars, especially in beverages and snacks, can flood the system, overwhelming the brain's metabolic balance. Children exposed to such patterns early in life may develop heightened sugar preference and metabolic imbalances that persist into adulthood, setting the stage for cognitive vulnerabilities later on. Understanding the time-sensitive, dose-sensitive nature of sugar's role in the brain could lead to more tailored public health guidance. It may be wise to emphasize adequate, high-quality carbohydrate intake during developmental windows while promoting long-term metabolic flexibility and insulin sensitivity through diet and exercise as the brain matures. Interventions such as intermittent fasting, exercise-induced glucose cycling, and ketogenic therapies are being explored for their potential to restore metabolic resilience and mitigate the effects of early sugar-induced damage. The challenge, then, is to strike a careful balance, ensuring that the developing brain receives the glucose it needs without promoting metabolic patterns that contribute to cognitive decline later in life. As with many nutrients, the impact of sugar is not defined by its mere presence, but by its context, quantity, and timing. Recognizing the double-edged nature of sugar in brain health offers a vital opportunity, not just to treat neurodegeneration, but perhaps to prevent it through smarter, earlier lifestyle choices.